Today we're going to tackle the little bit more difficult problem of dragging a box along a frictional surface at an angle. Now this is very similar to the problem of dragging a box horizontally, except for the applied force being at an angle is going to give us a little bit of a problem, but we'll be able to get through it. So it says this block is being dragged at an angle of 30 degrees above the horizontal with an applied force of 120 newtons as shown. The force of friction between the block and the surface is 30 newtons, and the block has a mass of 10 kilograms. What will be the resulting acceleration? So in any force problem, the first thing you want to do after reading the problem is to complete your free body diagram. We already have the applied force drawn in, so let's add some other forces. We know that it mentions a force of friction. I'm going to assume the motion is to the right. That means my force of friction will be to the left. We have a normal force of interaction between the surface and the block. That'll be directed up, always perpendicular to the surface. And we have a gravitational force between the earth and our block, which will be pointed down. So far, so good. Now, next step is always to pick a direction. Again, we usually want to choose one of our directions to be the direction of motion or the direction of the acceleration. In this case, I'll say to the right is my positive x direction, and up will be my positive y direction. And now I see the problem. My applied force does not fall into either of my directions. And the way we dealt with these problems is we always treat each direction separately, and we have a Newton's second law equation for the x direction and a Newton's second law equation for the y direction. But what do we do with our applied force? Now, if you think about applying a force at an angle, when you do that, you're really, in this case, if you apply a force the way it's drawn here, I'm really dragging this block, I'm pulling it to the right, and pulling it up at the exact same time. So I can model my applied force as if it's really two forces acting at the same time. So I'm going to model my applied force by a force in the x direction, which I'll call Fax, Fa with an x, the x component of our applied force, and his friend Fa, Fa so y, which is the y component of our applied force. So I can use one notation or the other. I can use my applied force and the angle it's applied at, or I can use Fax and Fa. I can't use both. But in this case, if we use Fax and Fa, we're going to see how it's much easier to analyze because Fax and Fa both fit into our coordinate system we drew. The applied force does not, but the Fax and Fa version of the applied force does. Well, the next question you might ask is, well, how do we find how big Fax and Fa are? And if you look closely, Fax, Fa, and the applied force make up a right triangle. And since these are vectors, we can use trigonometry to figure out how big the components of our applied force are. So Fax and Fa are called the components. So Fa is opposite our angle, so we can use sine with Fa. Fax is next to our angle, so we can use cosine. So we can say, using our laws of trigonometry, that Fax equals the applied force times the cosine of the angle. So in this case, that's going to be 120 newtons times the cosine of 30 degrees, which is about 104 newtons. And we can do something similar with Fa, except for Fa is going to use sine, so it's going to be 120 newtons times the sine of 30 degrees, which is 60 newtons. So now we have Fax and Fa, and we can use those in our Newton's laws equation. So now we can treat this just like our normal horizontally dragged block problem. We're going to draw a Newton's second law equation in the x direction, a Newton's second law equation in the y direction, and see what we get. So in the x direction, we have the sum of the forces in the x. That's going to be the x component of our applied force minus the force of friction, and that's going to equal m times a in the x direction. In the y direction, we have the normal force plus the y component of our applied force minus the force due to gravity, and that's going to equal m times a in the y direction. Now at this point you can go through and see if we can make any assumptions. Our main assumption here is that our acceleration is all in the x direction, so that means there is no acceleration in the y direction, so that can go to 0. And now we can go, okay, let's put numbers in and see if we can actually solve this. So let's start in the x direction. Facts we found that's 104 newtons. Minus the force of friction, which was given to us in the problem, that's 30 newtons, equals the mass of our block, which is 10 kilograms, times the acceleration. And I can write just as A because we know there's only an acceleration in the x direction, so I don't need to carry around the subscript. And I have everything in this equation except for the acceleration. I can do 104 minus 30 gives me 74. Divide both sides by 10 kilograms, and I get the acceleration of this block is going to be about 7.4 meters per second squared. And that's all the question asks for. But I'm going to go ahead and do something extra. I want to see how hard the block is actually pushing on the floor. So I want to see what the interaction force is between the surface and the block. That would be the normal force. I can go to my y equation and try to solve for that. So I don't know the normal force yet. Fay I do know, that's 60 newtons minus the weight, and it tells me the mass is 10. So I can go back and I can use my gravitational force equation. Force due to gravity, we'll use a local version, just m times g. So that would be 10 kilograms times 10 newtons per kilogram. Gives me a weight of this block of 100 newtons. That goes into the y equation. Minus 100 newtons equals 0. So the normal force must then be equal to 40 newtons. So again, this problem wasn't that much different than the horizontally dragged problem. There's one extra step over here in purple where we had to take our applied force and break it into components. Once we did that, we solved it normally like we did before. We just used our x direction to solve for the acceleration. And one other thing to notice is that in this case, the normal force was not equal to the gravitational force. There are a lot of problems where that's true, and your brain might get used to seeing that and try to assume it all the time. But remember, you can't assume that. That's only in special cases. So let the Freebody diagram tell you this. So remember, the way we work through these problems: read the problem, draw your Freebody diagram. Now we have an extra step where we can break up things into components if we need to. Once you pick your coordinate system, break up any forces that don't fit into your coordinate system into components so they do fit into your coordinate system. Use your picture to create your equations. These are not things you memorize. You create them directly from your Freebody diagram, and once you have that, you use your newly created equations with any other equations, in this case our gravity equation, to solve for whatever is missing.